All right, now I think a question that's natural to ask is, for G the symmetric group and chi lambda the irreducible character, corresponding to the conjugacy class of permutations having cycle type lambda, is there a nice formula for chi lambda of G? Sorry, let's say chi lambda of W because I'm thinking of these elements as permutations. The answer, unfortunately, is no. And that's too bad, because if the irreducible characters can be used to describe all characters of the symmetric group, then it would be nice to be able to evaluate them easily on the elements of the symmetric group. But unfortunately, there's no really nice formula. There is a formula. If you have really low standards, maybe you could call the existing formula nice, but I would say there's no nice formula. And we'll talk more about that later. So let's do an example with irreducible representations of S3. And the representation that we looked at last time, the defining representation, is not irreducible. But its character should be a non-negative linear combination of the irreducible characters. So, as I said earlier, one-dimensional characters are certainly irreducible. So if we look at, let's see, W equals E, S1, S2, S1, S2, S2, S1, S1, S2, S1. We've got the character called the trivial character. Now, I should also mention that the character of a one-dimensional representation is equal to the representation, because when you take the trace of a 1-by-1 matrix, it's just that matrix. So if we represent every element of the group by the number 1, then the trace is just the number 1. Then we've got the sign representation, which is -1 to the length. Now, this is a representation because sign happens to be a homomorphism. It's irreducible because it's one-dimensional. None of these ones or negative ones could possibly be a direct sum of smaller matrices. And there's another representation which I can put here, which is two-dimensional. So we've got the identity matrix, which is always what we assign to the identity element of the group, and then -1, -1, 0, 1, 0, 1, 1, 0, -1, -1, 1, 0, 0, 1, sorry, yeah, 0, 1, -1, -1, and 1, 0, -1, -1. Let's call this row 2 because it's two-dimensional as opposed to the one-dimensional representations. Its character, which I guess we can call chi2, is 2 is the sum of the diagonal entries here, 0, 0, -1, -1, 0. Now, we can see that this cannot be expressed as a non-negative linear combination of the other characters because of the negative ones here. There's no way we can take a non-negative linear combination of 1 and 1 and get negative 1. So the only way that this could be, we know that there's 3 conjugacy classes in S3. The 3 partitions of 3. So this couldn't be a non-negative linear combination of some other one-dimensional characters. Well, I guess it could be. There could be one other one-dimensional character, and this could be a linear combination of that and this. But actually, it couldn't be a non-negative linear combination of either of these. And it couldn't be a non-negative linear combination of just a third one. We could maybe use the third one-dimensional representation twice. But that wouldn't have a trace of negative 1/2 to be able to use twice. Actually, I'm using a fact I haven't taught you, that we're only going to get integers here. So, okay, maybe for the time being, just believe me that this one's irreducible. So here's 3 irreducible representations. And the defining representation trace was 3, 1, 1, 0, 0, 1. Now, if you believe me that these are the 3 irreducible traces of S3, then this has to be a non-negative linear combination of those. Well, the 3 could be 2 plus 1 or 2 plus 1, or even 2 of these plus 1 of those, or something like that. But the zeros have to be negative 1 plus something. So it'd have to be negative 1 plus 1 or negative 1 plus that one. So this would have to be chi2 plus either trivial or sine. Aha. If this value here is 1, we have to be adding 0 plus 1 rather than 0 plus negative 1. So this is chi2 plus the trivial representation. So one of these plus one of those. So indeed, it's in the cone generated by these 3 characters, the non-negative linear combinations of these 3 characters. The end.